is advancing localization, the sensing technology for 5G and beyond. Dr. Harish Viswanathan is currently the head of the radio system research lab in Nokia Bell Labs, also as a EEE fellow and a Bell Labs fellow. So, welcome.
Thank you very much. Thanks for organizing this and inviting me to speak here. So what I want to do today is give you a little bit of an idea of what we're doing in Bell Labs on localization and sensing, describe some of the experiments that we have been doing and what kind of results we are getting. So, okay, first of all, 5G has precise indoor positioning as one of the goals. And I think this is really relevant for the industries. We've seen multiple industries, especially in warehouses and airline manufacturing, aircraft manufacturing, where the rooms are so large that competing solutions like the ultra-wideband are not so suitable. They're very expensive because of the short range that they provide. So 5G turns out to be a good provider of localization for these kinds of environments. So here GPS is not available indoors, so obviously you can use GPS, but as I said, the other solutions like ultra-wideband are also not very good. And then in some cases, even for campus, it turns out to be useful, so it's a mix of indoor and outdoor environments. And then we do hear from the industries that, like Bosch, for example, a single system that does both communications and localization is also very advantageous. Okay, and then performance target, currently the goal is sort of 50 centimeter accuracy with 99% of the locations in the covered area being able to achieve that. Of course, there are other use cases maybe where we need even more accurate localization. So what we've done is actually experimented in this facility called Arena 2036. So for those of you who don't know, it's a manufacturing-like facility operated by the University of Stuttgart in Stuttgart, Germany, and a lot of companies come to that to experiment. So we have Bosch, Daimler, etc., experimenting with new types of manufacturing, and we are participating in that, and we've deployed our 5G radio heads. As you can see, there are six of them deployed, and I'll show you the distances between them, etc. And this is sort of a scenario of what it looks like in the arena. Okay, so what kind of results do we get? So first, this is just basic 5G before I move on to 5G advanced. So here you can see the 6 TRPs shown in black, and you can see the distance in meters. So it's about 20 meter by 15 meter or 10 meter sort of area. And each of these dots is where a measurement has been made to understand the accuracy of the localization. And you can see we followed multiple methods. So we have time of arrival, angle of arrival, and joint time of arrival and angle of arrival. The ML here refers to maximum likelihood, not machine learning. So time of arrival means that you're trying to estimate the range using the arrival time. And the angle is, if you have an antenna array, you can also estimate the angle. Time of arrival does not require an array antenna. So you can see that the accuracy we get is fairly good, like 50 centimeter, we can get up to 90% in this sort of setup. The key is line of sight. So it's very difficult to do localization if it's not line of sight, and so that's a hard problem to crack, and that's where I think the next idea using machine learning is going to show up. So if I move on, in 5G Advanced we have AI ML based positioning as a work item. The goal here is really to use novel techniques like machine learning to improve the localization accuracy. So all about improving the accuracy, especially for non-line of sight conditions. Right? So you can see if there's a block, then the signal doesn't have a direct path, then the estimation of the time of arrival won't be correct. And so how do you localize if you don't have that? So I think the approach we are pursuing is using AI ML directly with the received data. So you take the estimates of the signal, a position reference signal for example, and then directly apply machine learning there to see what kind of accuracy you can get. And with the same data that I showed you in the previous slide, data collected, we ran some offline experiments, and indeed, machine learning has a significant advantage because you train, of course, it's based on training in the same location with some training data, and then of course separate data for validation, the usual way we do machine learning models. And it turns out that accuracy improves quite a bit, and it can also do some non-line of sight locations. Of course, there's always some locations that are really hard up here, and the positioning error is much better compared to the angle of arrival type of methods. But there's one open challenge with the machine learning techniques, and this has to do with generalization. You train in a particular facility, and it works really well in that facility. But if you move and deploy the network in a different facility, and which we have done as well, experiments like that, so you change the data set and it comes from a different facility, then you find that machine learning doesn't do as well. And that's a challenge that we have to address, because it's going to be very difficult to train for each location. So, but if we are willing to do that, of course, then we can do really well. Yet another concept that's being developed in 3GPP is what is called carrier phase positioning. So here we take the time of arrival to the next level. Time of arrival tells us what the distance is for line of sight signals. But you can also estimate the distance much more accurately if you rely on the carrier phase. So this is now the RF carrier phase. So each little movement of this RF signal causes a phase change, and that's what this is relying on. But of course, carrier phase is very noisy, so it depends on the hardware on both ends, and so the technique is fairly complicated in the sense that you have not only a target UE but also a reference device, and both the target and the reference have to send double differential phase measurements. So, which means that phase measurements from across multiple sites, and then you do some processing based on the reference device as well as the target device. So that's how we can remove some of the phase errors, because the reference device is also making the same kind of measurements, and you know the exact location of the reference device. So again, the accuracy is super good, I would say, with this kind of a technique, if you can make it work. Some preliminary research using the same data shows that positioning accuracy can actually be under 1 centimeter even. Of course, because we are dealing with RF carriers that are in the 3.5 gigahertz. So any small movement is detected in the RF carrier phase. Okay, so those are some of the concepts and experiments on the localization. What is coming next is, of course, sensing. Here we think it's really apt for 6G, because we need wide bandwidths, which are going to be available in 6G in the sub, say 14 gigahertz. Today the 5G sub 6 gigahertz is 100 megahertz, and the resolution is limited. But if we go to wider bandwidths, then we can do a lot better in terms of sensing resolution. And the density of the network, we hope, will also improve over time. So that also will help sensing, because now you're closer to the objects that you're trying to sense. And then fundamentally, AI and signal processing and MIMO and beamforming are going to be part of 6G just for the communication itself. And so it's easy to reapply them for machine learning. And the goal, of course, is to create every base station to be able to sense in addition to communication. So you make sensing available everywhere. I won't go through the use cases. I think the previous speaker did a great job of pointing out all the different use cases in the 3GPP. So from a technical point of view, we do see a lot of challenges. And I think there's another reason why we want to wait till 6G. Gives us more time to solve some of these challenges. The first one is the hardware reuse. So if you want to use the same base station, then you need to enable that with some kind of full duplex capability. And that is not easy. And so we have to have multiple panels and things like that. And there's ongoing research on saying how to make some of the antennas available for sensing capturing the reflected signal while some of the antennas are doing transmission. Then we have like joint resource allocation problems. So the scheduler design, which is really important from a QoS perspective, should now also take into account resource allocation. And then the beam scanning, how you do that for sensing versus communication. I mean, if your traffic is located mostly in one area, you still have to scan all the areas, like we do with the SSB beams. So how do we exploit that for sensing? And of course, we have to work on the processing algorithms, which extract delay and Doppler, and from that identify objects, etc. So there's still a lot of technical work left to be done here. So if you look at the 3GPP, the first phase in release 19 is about channel models for ISAC. And our work here is using a channel sounder. So what you see on the left here is a channel sounder with a transmitter and receiver, sort of in a monostatic type of setup with isolation. And we've gone around making systematically a lot of measurements in different types of environments, like rooms with metal furniture, large cafeterias, and then number of different locations where measurements were made and the size, etc. And what we have done is capture the return power from the clutter, right? So you're not really sensing in these measurements, you're not actually sensing a target, but you're trying to understand what the return power is so that you can model that in PGPP context. And what we observe is the return power really depends on the size of the room. Obviously, the larger rooms have smaller return power compared to the smaller rooms, right? But it's these are CDFs of the return power over here, basically. And then you can see that the small offices have the most return power, whereas the larger rooms have smaller. And so we can now come up with a model, and these vertical lines you see is kind of the model that we adopt for the different room types, and this helps us to sort of understand what the signal to noise ratio is you can expect to get in a sensing system, right? And we'll be making some proposals to PGPP. Of course, it will be much more complex models, but this is one of the measurements to back up the models. Okay, and then from an architecture point of view, and that's the other work that was talked about earlier, the SA2 will start working on sensing. And here I think there are some new things to do in terms of the architecture. We need a sensing management function, just like the location management function, which would take input from the base station and do some processing, etc. And then there may be also a role for the ORAN RIC, the RAN intelligent controller, because you can think of near real-time optimizations with the sensing data, things like sensor fusion with other sensing, machine learning based processing for identification, etc. could be happening off the GNOD. But then the important thing is also the interface between the RU and the base station. We need to send additional signals like the frequency phase signals, because a lot of the processing in MIMO happens at the RU. So all the frequency offset correction and channel estimation, all of that happens there. So you need the right kind of signals sent back for the sensing processing. And also, if you're relying on multiple nodes to do the sensing, then synchronization between them. Like for example, if you had a separate sensing receiver, then the transmitter and the receiver need to be in sync. So these kinds of things would need new interfaces. Okay, and then another concept that's related is what we call the radio-aware digital twin. So this would be to map the environment facilitated by the sensing to build a digital twin. And this can then be used to enhance the communication itself. So for example, we can do things like overhead reduction and blockage prevention, etc. because we have an accurate map, radio map, and so if an AGV is moving behind a big blocker, then we can detect that just from the digital twin, predict that, and then take some corrective actions before the blocking actually happens. This of course cannot rely only on sensing, but sensing is part of the story here, I think. We'll of course have the very good maps of the rooms, the objects there, but then the objects move, so you have to account for all that when you create these real-time digital twin maps. Okay, so now I want to just show a little video of what we have done to conclude my presentation here. So in terms of the video, let me see if it plays.
We are at the ARENA 2036 Industrial Research Facility, where we have deployed our prototype system for joint communication and sensing. The signal is being sent out and it's being reflected, at least in parts, by the environment, including the robot itself. The reflected signal is being processed in the sensing processing unit, where we can obtain the distance, range and reflective strength of the robot, which we then visualize in the radar view on the screen.
Okay, so with that, let me summarize what I just spoke about. So I think 5G is a great technology for positioning. We started with the angle of arrival and time of arrival sort of methods, and moving on to now AI, ML and carrier phase positioning to increase the accuracy. And we are seeing real traction in the market for such solutions. And then network as a sensor is a bit more exploratory, probably for 6G. It has potential for many use cases, which was spoken about in the previous presentation, but there are also a lot of challenges that we have to overcome before sensing really takes off. You know, we have to know for what use cases we can provide performance that is acceptable. You know, it's never going to be 100% accurate, so it's about what is the accuracy that's acceptable for that particular use case. So this is still a lot of investigation left to be done. Thank you.
Thank you. Thank you, Harish.